Okay, hello everybody, and thank you for joining us today. Hi, I'm Nick Taylor, the editor of Spectroscopy Now, standing in for Microscopy and Analysis Julian Heath, who can't be with us today. But I'm here today to introduce this webinar entitled Multiscale Correlative Microscopy of Energy Storage and Conversion Devices. And today's webinar is brought to you by ZEISS Microscopy. And we're pleased to have Drs. Paul Shearing and Arno Merkel joining us here today as your presenters. Paul Shearing has an M.Eng in Chemical Engineering from the University of Birmingham and a PhD from Imperial College in Earth Science and Engineering. And he's currently a senior lecturer in Chemical Engineering at the University College London. Arno Merkel received his PhD in Materials Science and Engineering from Northwestern University in 2007 and currently oversees correlative imaging and X-ray microscopy for the materials science market segment at ZEISS Microscopy. So, Paul and Arno, a very warm welcome to you both today.
Hi.
Thanks, Nick.
Good to have you both with us. Now, just before we get started with today's event, let me just remind everybody, of course, that this is an interactive web seminar, and so feel free to ask questions at any time during the presentation by clicking into the questions box. Now, only our presenters will be able to see your questions, so don't be too shy about asking them. Now, the questions will be answered during a Q&A session at the end of this 45-minute presentation as time permits. However, if Paul and Arno aren't able to get to your question today during the live broadcast, then they'll follow up with you later offline. So without further ado, let me turn the floor over to Arno Merkel, who will begin our webinar today. Okay, Arno, it's over to you.
Nick, wonderful. Thank you so much. Well, this webinar today, we will be discussing, my name's Arno Merkel, of course, thank you for the introduction. We'll be discussing some multi-scale characterization techniques specific to energy storage and conversion devices. And thanks for this opportunity to be able to present to you today. I'd like to start off typically with an image. What you're seeing here on the screen is a scanning electron microscopy image of a cathode particle. This is a lithium-ion battery cathode and LCO material. And what you're actually seeing here is an individual cathode particle, a few microns in size, and it's demonstrating some of the low KV, low energy imaging capabilities. And in particular, what we're looking at are some of the more lighter or less dense materials, and seeing the conductive additive and how it's agglomerated, inhomogeneously agglomerated, kind of there on the upper left of the image. We'll be focusing in a few other dimensions a little bit later today, and taking a look at the third dimension as well as the fourth dimension of looking possibly over time as well. But this gives you a bit of a flavor for the final state here of some of the analysis that's often performed, and really pointing to a multi-scale approach. This is one individual cathode particle within presumably a large electrochemical device, a battery that you hold in your hand or is in your car or in your laptop. And so we'll look at strategies of how we make sense of this combined multi-scale challenge and how we begin to overcome that. So with that, I'd simply like to dive into the agenda. I'm going to kick things off just for a few minutes, maybe 4 or 5 minutes here, with an introduction. I know this is a microscopy forum, and I'd like to introduce a few of the length scales and techniques of some of the applications that will be shown. Paul will then take it over for the middle section here and specifically show a number of studies, primarily on X-ray microscopy that he's done in his lab in London, looking at both fuel cell but also battery materials. And then we'll come back at the end for 10 minutes or so and kind of have an outlook here of how we make sense of the diverse and multi-scale nature of these data sets, and as I said, forming kind of strategies for building experiments that require characterization across several length scales. So with that, let's dive in. What I'd like to show first, combining some of a collage here of various images from battery materials. This multi-scale problem that we're looking at, if we start in the upper right in our ruler here, we're looking really at the macro scale, and we're looking at packaging and assembly type devices at many microns of resolution, things that gross defects, and looking at more engineering type of approaches. But as you slide down the scale, of course, you require different techniques. And in the way you have different assemblies of particles, you can study particle shape and sizes, but as well as layer quality and bulk defects before you get to the particle size. But eventually you also want to perform probably porosity or transport measurements, and then even more finer individual particle defects, but also make sense of how that is representative or not representative of the assembly as a whole. So in that sense, I'd like to point to the diversity of techniques that are often required, and of course not all techniques are required for every application, but you have to judiciously pick which 2 or 3 are the right approach that give you the appropriate combination of resolution, but also contrast mechanism and also a dimension. Perhaps the 3-dimensional information is necessary for a particular study. Some studies, perhaps only a 2D information is sufficient. So having that palette to choose from is really essential. And what we're showing here on this graph is effectively the approximate resolution scale, where we're looking at micron or microns of resolution using either stereo light microscopy or submicron X-ray microscopy, spanning all the way down through the various light and electron techniques and X-ray techniques to the sub-nanometer as well. So we'll focus on a couple of these here today, namely X-ray microscopy and focused ion beam scanning electron microscopy. And to give everyone just a bit of a primer on the background so that it's understandable in a context, I'd like to look at a graph here which really plots the approximate space in which sample size and 3D voxel dimension converge. We're focusing on, of course, battery materials or energy materials in general will have relevant investigations across a great scale here and extend beyond just these blue boxes within here as well. What we're looking at now is from approximately the meter sample size all the way at the top using more industrial-based CT approaches to the very finest scales in the lower right. The essential part here is the connectivity of 3D approaches and linking all of these scales and making sure you don't have gaps in between these so that you have this palette effectively to pick and choose where the experiment makes sense. To give a bit of a background, we are going to take a look at each of these 3 relevant techniques in blue: submicron X-ray microscopy, nanoscale X-ray microscopy, and focused ion beam SEM. All 3 of which are 3-dimensional techniques, the 2 in the upper left or the 3 in the upper left here being non-destructive, meaning of course you can re-image certain regions at different resolutions or contrast mechanisms prior to sending it down this chain. Typically you're moving down and to the right in this chain and judiciously selecting regions for further characterization. We'll get back to that concept toward the end once we wrap up. What I would like to show briefly is some of the work, a primer of some of the work that Paul will be showing and I'll be showing a little bit later, comes from Microscope platforms that such as these. This is the ZEISS Xradia Versa platform, which is really pushing the limits of resolution and contrast for X-ray imaging in the laboratory, really rivaling some attempts at synchrotrons around the world in terms of resolution and contrast. Paul will discuss this in a really tangible way with some of his experiments in a few minutes. And critically, in implementing here optical methods as well, and having kind of a dual-stage magnification mechanisms allows one to achieve these resolutions and also perform microstructure evolution studies, seeing how the same sample evolves over time and quantifying that in 3D. Just a couple of the architecture bits and pieces within here gives you a bit of a layout. Looking in the upper left-hand side, for those of you not familiar with the technique, we're essentially just sending X-rays through an object, which is then rotated on a stage. You typically rotate this through 360 degrees, and 2D radiographs are acquired, and that's then computationally reconstructed. And primarily, we see quite a bit of work here done in a variety of different shapes and sizes of samples, as you saw in the previous graph, using different unique modalities, both absorption contrast, but also extending to phase contrast, and also a new modality, which we won't go into today, but possibly for a future webinar, is looking at diffraction contrast, where we can get grain orientation from materials. Now, moving on from this length scale, we're now able to implement a related approach, a similar in concept, a similar approach, but now we're looking at much higher resolution incorporating X-ray optics. And here we're effectively able to go down to 50 nanometer spatial resolution in the Ultra, the ZEISS Xradia Ultra, 50 nanometer spatial resolution in 3 dimensions, measuring, including the incorporation of condenser lenses and objective zone plates. Following this approach, we will touch at the very end on some focused ion beam techniques. I won't dwell on this right now because we want to get to some of the scientific studies. But as many of you know, focused ion beam has a wide variety of different application spaces, including basic imaging or cross-sectioning of samples, also used for sample preparation, such as lamella, but other structures such as needles. And here we see even a pillar here, which is being used for compression studies. But what we'll focus on today, you also see some nanopatterning capabilities. We'll focus toward the end of this talk on more tomographic techniques and how, at this length scale, how this complements some of the work being done at the larger length scales using X-ray microscopy. So with that, the ZEISS Crossbeam is capable of all of these basic areas of investigation with a diversity of applications in each of these. And we're really focusing in on tomography a little bit later in some of the specific use cases in energy materials. So with that, this is really meant to enhance applications and really provide maximum information through the use of multiple detectors, also simultaneous acquisition using various detectors, and really maximizing throughput for relevant volumes and relevant resolutions that are needed, and spanning a variety of those, and really providing best 3D resolutions in the way that's achieved in both platforms, in both the 340 and 540. Now, we won't go into the details of how that's achieved today. We really wanted to keep this focused on some of the science and some of the application areas. And with that, I think my brief introduction section is over. I'm going to pass this over to Paul now, who will dive into a few of the studies that he's been doing over in London. Paul, it's all yours.
Thanks very much, Arno, for that great introduction. Hi, everyone. Thanks for the opportunity to present some of our work to you today. This is my first webinar, and I think it's really exciting to be able to connect with people all around the globe and tell you all a little bit about what the investigations we've been doing in collaboration with ZEISS over the last sort of 5 or so years, and particularly to apply X-ray microscopy to electrochemical devices. I should mention that most of the talk is going to be on sort of X-ray microscopy and tomography, but at UCL, in addition, we have a suite of ZEISS focused ion beam instruments, and we're really excited to explore the capabilities of the correlative microscopy opportunities with X-ray microscopy, ion beam microscopy, as well as the light microscopy that Arno mentioned. And I know that later on today, Arno will sort of look towards the future and the intelligent ways that we can combine all these different modalities to begin to get a multi-lens scale, a multi-time scale, and a multi-modality approach to materials characterization. So I think it's really exciting opportunities, and as myself, as a chemical engineer working in the field of energy materials, I can see a whole host of problems that we can begin to tackle with these suites of materials characterization tools that we have. Today I'm going to focus on electrochemical devices, and most of that time I'm going to be spending talking about lithium-ion batteries. Arno's already given an overview of capabilities, so I'm going to skip over that relatively quickly, and I'm going to talk about the application to generic electrochemical devices, fuel cells, batteries, flow batteries, etc. I'm going to spend the majority of today's webinar looking at some case studies for imaging lithium-ion batteries across multiple temporal and spatial resolutions, and hopefully we'll see why that's so important for these lithium batteries that we've all become so reliant on in recent years. And I'm going to aim to highlight the complementarity of the lab systems as well as synchrotron systems that we still use, and perhaps pose some challenges for the microscopy community to think about how we can continue to bridge these time and length scales in an even more integrated fashion to tackle some challenges in energy materials. As Nick said right at the beginning, please do feel free to type in with questions. Arno and I are keeping a close eye on the attendee questions as they as they come in, and we're going to try and leave as much time as possible at the end to answer all of your questions. And again, as Nick highlighted, for those of you that we don't have a chance to answer today, we will make sure that we follow up on those questions. I should say that as well as UCL and ZEISS, so I'm obviously at University College London working in the Electrochemical Innovation Lab. Arno and his team at ZEISS, we've been collaborating for many years now. But this is a team effort that extends across many institutions and many different countries. And it's impossible to acknowledge all of the individuals individually, but just to say thanks to all of our collaborators and funders who contributed to this work. The main question that I want to try and address today is how can we use X-ray microscopy to design better electrochemical devices? Electrochemical devices is kind of an umbrella term that we use to describe fuel cells, batteries, redox flow batteries, supercapacitors, which are at varying stages of commercial development, but actually share a lot of common traits, particularly in the porous functional materials that we're exploring when we're developing and designing these electrochemical devices. So what do I mean by a better device? Well, safety is obviously very, very important. We want to mitigate against the risk of failures in lithium-ion batteries and fuel cells. We want to promote power and energy density to make our batteries last longer and discharge more and more quickly, so we can spread these to a variety of different demanding applications. They need to be more durable. If we take the lithium-ion battery as a great example, these were developed by Sony in the late 1980s and early 1990s to power consumer electronic devices like camcorders. If you go to a showroom today, you can buy a Tesla Model S, which has something like about 7,000 individual cells within that Tesla Model S automotive powertrain. And we're asking these batteries to deliver more and more demanding applications such as automotive powertrains, grid-scale energy storage, as well as space exploration, unmanned aerial vehicles, biomedical applications, all using the same basic chemistries that were developed in the 1980s for the consumer electronics business. So we need to take those existing material sets and indeed new material sets and use the X-ray microscopy and correlative microscopy tools in order to engineer the best possible device for a very broad range of very demanding applications. I mentioned that I'm going to focus today almost solely on lithium-ion batteries, but in the Electrochemical Innovation Lab at UCL, University College London, we have a wide variety of electrochemical device research, and because we have the capability with the Versa 520 and the Ultra 810 to perform multi-scale correlative X-ray imaging, we apply these techniques to a whole variety of different functional materials. So, for example, here you're looking at a solid oxide fuel cell anode, which has been imaged at multiple length scales, from the microtubular device right down to the individual electrode particles. We look, in addition, at polymer electrolyte fuel cells. Here you can see some gas diffusion layers and microporous layers that have been imaged in situ. Again, one of the beauties of the non-destructive X-ray computed tomography techniques that Arno introduced is the ability to study materials under simulated operating environments. And we look at GDLs, for example, gas diffusion layers for fuel cells under compression and at different temperatures. We have a lot of recent work in understanding performance microstructure relationships for redox flow batteries. Again, another great in-situ application where we can look at the ingress of electrolyte into these complex carbon fiber woven materials. And as well as lithium-ion batteries, we do a bunch of different battery chemistries like lithium-sulfur, sodium-ion, and increasingly more novel and far-off chemistries like lithium-air. All of these porous materials and the microstructure of these porous materials will have a huge influence on the performance of the device. And so we're very keen to apply these imaging techniques to the broad spectrum of electrochemical energy materials that we're researching today. As I said, in today's webinar, I haven't got time to sort of touch upon each of these in any real detail, but do feel free, please, when you're asking questions, if you want me to elaborate on any of these areas in addition to the lithium-ion battery material that I'm going to focus on, please do feel free to ask. Okay, so back to lithium-ion batteries. Oh, no, sorry, one quick slide just as an advert for a recent journal article that we published in the Journal of Microscopy, because we often get asked, why are we doing these experiments in 3 dimensions? People have got on just fine in sort of the previous sort of 20 or so years using scanning electron microscopy and other 2-dimensional microscopy modalities. Why are we interested in three-dimensional characterization? Well, of course, SEM and other surface techniques remain a very, very valuable resource to use when we're studying these electrochemical energy materials. But we did a very extensive investigation of the comparison of stereological two-dimensional characterization techniques with these three-dimensional tomography techniques for lithium-ion batteries in order to demonstrate really the power of 3D microscopy to solve some of these phenomena of these performance microstructure relationships that are really reliant on percolation behavior. And so without sort of the time today to go into the detail, I would sort of just point you towards this recent paper, which goes into some significant detail about why it is that we're often interested in three-dimensional characterization when we're looking at these porous, complex functional materials. Okay, so what happens when things go wrong? I mentioned I wanted to design a safer lithium-ion battery, and you might think, well, I walk around every single day with a lithium-ion battery in my pocket, and generally speaking, nothing goes wrong. And that's absolutely right. These are fantastically well-engineered materials. However, as we move to more demanding applications and to more demanding operating environments, when things begin to go wrong, they can be quite spectacular. The image that we saw there was an explosion of an 18650 lithium-ion battery cell, and it was the thermal image which showed the nucleation and propagation of heat through a battery as it leads up to failure. And just that thermal image, I think, is an indication of some of the challenges we face as materials scientists and engineers in making these batteries as safe as they possibly can be. Now, thankfully, these failure events are extremely rare. As I say, we all walk around every day with lithium-ion batteries powering our phones and our laptops. Increasingly, we see lithium-ion batteries in automotive applications driving around on the streets. And thankfully, these events do not happen very often at all. But when they do happen, it's a big news story. People will often remember the Boeing Dreamliner accidents that occurred in sort of 2012 and 2011, where some lithium-ion battery fires on board the Boeing Dreamliner actually caused the whole Dreamliner fleet to be grounded. And so we're keen to make sure that these rare events become even rarer, and our toolkit to tackle these and understand these failure events really hinges significantly on the microscopy and tomography tools that I'm going to talk about today. So a quick look at the lithium-ion battery fundamentals. Most lithium-ion batteries will have a graphite anode. This graphite is mined and it's printed onto electrodes in a process that is not at all dissimilar to the way in which newspapers are printed. This is a roll-to-roll printing process that occurs at many meters per second in extremely high volume. Similarly, for the cathode, we normally have a metal oxide or an olivine-type structure, which is printed onto an aluminium current collector, again on a roll-to-roll process. And as we charge and discharge the lithium-ion battery, we shuttle the lithium-ion from one electrode to the other. Now, about 4 billion cells of this nature are made every single year with little or no microstructural control. Consequently, the heterogeneities that within these structures are quite common. And it's our hypothesis that the microstructural heterogeneities intrinsically link to the degradation and failure of these devices. Demanding applications like automotive, like grid-scale storage, like niche applications for space and military require intelligent engineering strategies to develop new porous materials that can operate safely under a very broad range of demanding applications. Why are we using X-ray image to study these energy storage materials? Well, I've already mentioned failure mechanisms as a key performance issue, but also as we move to larger and more expensive battery packs, we want to overcome capacity limitations and we want to prevent lifetime degradation. The imaging requirements for us are that it's non-destructive, ideally, there's penetrative, so we can see what's happening beneath the surface of the battery, and it's possible over multiple time and length scales. Here we're looking at a similar 18650 cell, which is a commercially available cell. At the macro scale, we might be interested in device architecture, which maybe has length scales of millimeters down to microns. At the micron to nanometer length scale, we have microstructure effects that are associated with the efficiency of transporting lithium ions through this complex porous structure. And then at the finest length scales, from the microns down to the nanometers, and maybe even single nanometers, we are interested in exploring chemical decomposition effects. Once we are able to effectively combine all of these length scales in a non-destructive X-ray imaging modality, of course, there's a very valuable opportunity at the end of life to do post-mortem imaging as well. And Arno's already pointed to the focused ion beams using gallium ions and helium ions, which enable us to image at really the very finest resolution to explore some of those nanometer and maybe even sub-nanometer microstructural features. So this is what an 18650 cell looks like when we strip it to pieces. 18650, by the way, is kind of battery terminology for a cell which is 18 millimeters in diameter and 65 millimeters high. These were originally developed for applications in laptops, and normally in a kind of traditional laptop battery, you maybe have 3 to 6 of these 18650 cells. As I've said, companies like Tesla have directly translated this architecture and this chemistry into manufacture of automotive battery powertrains. And now if you buy a Tesla Model S, you might find up to 7,000 of these Panasonic 18650 cells within your Tesla drivetrain. And so we've taken one of these Panasonic NCA cells and we've done a full body scan using the Versa 410 to get a full picture of the architecture of the cell. Here we're looking at just a single slice through the body of the cell, which shows something about the cell architecture, the spiral wound electrode structure, the various current collectors and safety devices. Without depackaging the cell, we're able to do a region of interest scan, again using the Versa 410 instrument, to just highlight a higher resolution an individual section of that battery. And this cross-section here shows from that region of interest scan exactly the level of detail that we can extract. We can begin to look at the individual electrode layers, cathode, anode, the separators, and the current collectors. And then when we decide we want to depackage the cell, we can move the electrode material onto the Versa 520. Here we're looking at the nickel-based cathode material with a much higher resolution, a 350 nanometer voxel size here, and beginning to reveal something about the detailed microstructure of the electrode. And then by passing it from the Versa onto the Ultra 810, we can conduct region of interest scans with voxel sizes down to 16 nanometers. Here we're looking at a voxel size of 130 nanometers, but we can improve that by nearly an order of magnitude. Importantly for these multi-scale images, we're extracting information about the architecture of the cell, about the nature of the material, about the chemical decomposition processes at each of those length scales. As I've mentioned, X-ray tomography is for us a really fascinating and powerful tool because it's a non-destructive tool. And this means that we can characterize the same microstructure or the same device at different stages within its life cycle. And we can also look at failure and degradation mechanisms that occur over different timescales. We've already talked quite a lot about the different length scales that might be associated with lithium-ion battery research, but it's also important to think about the different timescales that might be associated with lithium-ion battery research. Here's a diagram which was from Phil Wither's recent paper in International Materials Review, and it's called Quantitative X-ray Tomography. It's a fantastic review article, and I really recommend it to you all. And what Phil and Eric Mehra here have done is compare the spatial resolution with the acquisition time for a range of different synchrotron sources, and also for a few lab sources. And I've highlighted here the Xradia ZEISS Ultra and the Xradia ZEISS Versa. I think that should show up hopefully on the next image, where you can see we've circled those instruments, which are the lab instruments that we have here at UCL. From a battery perspective, we're interested in timescales that span from milliseconds, which are associated with the catastrophic failure, the explosions that we saw in that thermal video right at the beginning, through to many thousands of hours. If you buy a lithium-ion battery-powered car, you would expect probably to have a warranty somewhere of the order of about 7 years. And so there are many orders of magnitude, more than 10 orders of magnitude in terms of the time scales that we need to probe, as well as many orders of magnitude in the length scales that we need to probe, and I've highlighted that already. And I think that the interesting thing here from the application of X-rays to tackle some of these things is sometimes we want to go to a synchrotron because we're interested in doing very, very fast imaging, sub-second tomography to capture some of these dynamic events. But often, if we're interested in degradation studies, we need to study the materials and microstructure evolution over many tens, hundreds, and maybe even thousands of hours. And the improved availability that we have because we've got these X-ray instruments in our lab means that we can schedule experiments to tackle some of these degradation questions. And I hope I'll be able to show you a few examples of that as we move through today's webinar. Okay, so let's have a look at some examples of imaging operational lithium-ion batteries. And the first example I want to highlight is a paper from a couple of years back that we published in Advanced Energy Materials. And it was an operando study of the charge and discharge of a small Panasonic ML414 cell. You can see the top of the slide obviously shows the cutaway X-ray image, and at the bottom is a photograph that shows just how small this cell is. These cells are sometimes found in memory backup applications, but increasingly we're finding cells of this geometry powering medical devices such as pacemakers, which are obviously very mission-critical power sources. If we take a look at the methodology, we took this Panasonic ML414 cell, which has a manganese-based cathode material. Again, you can see the cross-section from the grayscale image that we reconstructed using the Xradia Versa instrument. And the micro-CT that we were able to conduct here was able to give us sufficient detail of the electrode microstructure that we were able to track the evolution of that electrode microstructure as a function of the state of charge of the battery, whether the battery was charged or discharged, and as a function of the lifetime of the battery. And of course, that lifetime issue is really super important when we're looking at devices that are powering pacemakers. The next slide just shows a video that takes us through some of the imaging, and we can see the coin cell is just, hopefully you can make out, just set on top of that nail right next to the X-ray detector. So the first tomography we took had a 5.6 micron voxel size, and we're able to subsequently do a second tomography, which is a slight region of interest tomography, to study more of the detail of the electrode microstructure. Again, it's a non-destructive technique, so all of the usual electrochemical spectroscopy tools that we apply to study these batteries can still be used in tandem with the X-ray imaging. So here's the electrode with a 5 micron voxel size, and soon the video will switch to the more detailed region of interest scan where we have a 1.2 micron voxel size. And at this resolution, you can see the blue cathode particles and the electrolyte and sort of get an indication of the significant detail that we can extract from these scans. The granular battery electrode will breathe. It will expand and contract as it charges and discharges. As the manganese material is going to accept lithium, it will begin to expand, and then as it donates lithium back to the counter electrode, it will shrink in response to that. And this continuous breathing, this expansion and contraction, is one of the main mechanisms for microstructural degradation in batteries, which also leads to performance loss. Because this is a non-destructive technique, we were able to use the images in combination with digital volume correlation, that is three-dimensional digital image correlation, to compare the charge and the discharge state. By comparison of the charged and the discharged battery, we're able to generate three-dimensional strain maps, which gives us an indication of the direct link between the mechanical degradation of the battery, the image of the battery, and the electrochemical performance loss. And this is the first time it was able to be done by using these unique non-destructive X-ray microscopy tools. Furthermore, because we have significant detail about the cathode microstructure, we're able to analyze the cathode on a particle-by-particle basis. And this means we can tell which part of our electrode is working the hardest. Where is the lithium most likely to transport to? Which particles are most likely to accept the lithium and give the lithium and at what rate? And in doing so, we get a direct linkage between the electrochemical performance and the microstructure, and this gives us then a really powerful tool to design higher performance batteries. Of course, it's not just commercial cells that we're interested in. We do a lot of materials development for batteries in our own lab, both in silicon and graphite and other novel materials. And we've developed an in-house cell geometry which enables us to make bespoke cells which are effectively X-ray transparent. So we assemble cells in these PFA swage block geometries, and we're able to change the chemistry, change the morphology, and again use X-ray microscopy as a tool to understand microstructural evolution. So here we're looking at a silicon anode, but I believe the next slide should be on a graphite anode. And you can see again here we've got some cross-sections from that graphite anode material at various stages in the cell lifetime. The top of the cell is a lithium metal electrode. The bottom of the cell is a graphite electrode. And we're shuttling the lithium ions from top to bottom and top to bottom as we're charging and discharging. Again, I highlighted that whilst failure can be catastrophic and occur over very short timescales, degradation is something that happens over many tens, hundreds of cycles, and therefore over many tens, hundreds, and even thousands of hours. Here, using the Versa 520, we're able to study the evolution over 10 and up to 70 cycles on this image to see exactly how those material microstructures are evolving under normal use conditions. And this gives us a unique insight into their degradation. And it's not just at the micro scale that we're interested. We also, as I mentioned, have an Ultra 810 at UCL, which we can use in tandem with the Versa to get higher resolution images of the real microstructural detail of some of these complex and highly heterogeneous materials that go into everyday lithium-ion batteries. Here we're looking at some cross-sections from our Ultra 810. On the left-hand side, we have an absorption contrast image. In the middle, we have a cross-section from a phase contrast image. And on the right-hand side, we have a combination of both images, which enables us to leverage the benefits of absorption and phase contrast microscopy to get a combined image to get these kind of beautiful and very detailed pictures of the nanoscopic structure of these graphite electrodes. So, as I've said, it's a fascinating multi-length scale and multi-time scale challenge that we're trying to address. For the last few slides in my section of this webinar, I wanted to look at what can happen if we can improve the time resolution, and in particular highlight the complementarity of the lab-based X-ray microscopy with the synchrotron X-ray microscopy, whereas we know because of the much improved brightness of the X-ray source, we can image in tomography at a resolution of sort of tens of microns, perhaps in sub-second. I'm going to present some recent work from the ESRF beamliner ID15, where we're able to conduct tomography in about 250 milliseconds. And by doing this, we're able to, and by conducting tomography at such fast timescales, we're able to explore some of the most dynamic changes that are associated with lithium-ion battery failure. So here again is a kind of full-body scan of an 18650 cell. We're going to heat that cell up to about 240 degrees centigrade in order to initiate a failure that's going to cause an explosion. And at the end of the day, this is what the battery looks like. As I say, these failures are thankfully speaking, very, very rare. Here's some radiography images from that experiment where we're able to image at about 1250 frames a second as the lithium-ion battery is heating up and eventually undergoing a thermal runaway reaction, which causes catastrophic failure. We're looking at one half of the spiral wound cell here. The central portion of the cell shows on the right-hand side, the inner cylindrical support. Towards the middle of the image, you can see at this point that there is some significant changes to the battery architecture, and the copper is melting and the electrodes are beginning to degrade quite violently. And yet on the far left-hand side of the image, the cell appears to be, relatively speaking, quite unchanged. This video has now been playing for 20 or 30 seconds in real time, but actually, because it's a high-speed image, it only captures about 0.6 of a second, so 600 milliseconds so far of events. So you can see that these processes are really extremely rapid, and again, by combining the high-speed radiography of a synchrotron with the high-resolution tomography that's available to us in a lab source, we can begin to understand how these batteries fail, and ultimately design strategies to mitigate against this failure. So I'm going to close by exploring how this can be translated to lab tools. Well, if we look at a slightly different battery here, we've got a lithium polymer cell which has undergone a high voltage failure. This is a full body scan of that battery before failure on the left-hand side and after failure on the right-hand side. Similar to the radiography image you saw on the previous slide, you can see these purple blobs are forming, which is degradation of the copper current collector, which is agglomerated. This means these batteries see very, very high temperatures, high enough to melt copper. And as we go down the length scales again, we can compare the microstructures before thermal runaway with a voxel size of 420 nanometers on the left-hand side and after thermal runaway on the right-hand side. And by applying various image analysis and quantification tools, which I don't have time to go into today, we can understand exactly what the consequences of thermal runaway are and ultimately design strategies for microstructures and morphologies that might prevent these failures from occurring. For example, in this image, we were able to identify on a Versa 520 extensive particle cracking. If we took this then from the Versa and put it into the Ultra, at the highest resolution, we can see that we've got a significant morphology change, but also a significant chemical change within the cathode material for this lithium cobalt oxide cathode. And so this is all building up a very colorful and rich picture with data from different time and length scales, different imaging modalities that enable us to try and prevent these failure occurrences from happening in the first place. So to conclude, in batteries, there are many time and length scales and heterogeneities that occur across all those time and length scales. X-ray tools, I think, provide a unique, non-destructive platform to explore these microstructural evolution effects. But combining non-destructive tomography with focused ion beam slice and view, with helium ion microscopy, as well as with the spectroscopy tools that we're used to as electrochemical research scientists, we can gain an improved knowledge of the microscopic behavior of devices, providing new metrics to evaluate and compare materials and optimize their design. With that, I thank you all for listening, but I'm going to pass back over to Arno to wrap up. Those are my contact details. Of course, as we mentioned, we're very happy to take questions at the end of the webinar as well. So over to you, Arno.
Excellent. Thank you, Paul. Great review of some of the work that you've done in collaboration with a number of groups. In the coming few minutes, I'll keep the final section short here so we can address a couple of questions relatively quickly. I'd like to discuss some of the outlook and some of the current activities also of how we make sense of the length scales that we've looked at now, but also drive down even further to higher resolution, and how we really make sense of both planning a strategy for acquisition, but also combining the information from all these in a spatial context. And so we've talked quite a bit about different length scales here, but what really is this multi-scale challenge? Or is it just a multi-scale challenge? And of course you have examples, as Paul nicely showed, of mechanisms that occur across a variety of orders of magnitude and spatial resolution, obviously temporal as well. But the practicalities as a microscopist is that you often choose your experiment or your characterization based on the contrast mechanism. What types of information? Is it just density I'm after, or do I need some other types of information, some chemical information? So the choice of that is quite necessary as well. Beyond the modalities, you also have to ask yourself questions about what types of dimensions. We saw some nice digital volume correlation work that Paul showed on the coin cell image. Is simply 2D enough for a given experiment, or do we have to extend to 3 dimensions, or even the 4th dimension, looking at that time study? And then, of course, some of the practical considerations here is that obviously you have to, no single instrument is magical and able to cover all these scales and modalities and dimensions. We have to plan strategies and approaches also for performing that, which are oftentimes run by different users, both on campus or in the laboratory, but also your collaborators around the world. So at ZEISS, we're really dedicated to continually developing solutions that also enable this type of multi-scale and modality and dimension challenge to be addressed, and more seamlessly be able to acquire effectively and study these length scales in not only heroic experiments, but in those that can be done in a routine way. And so we're really moving toward this modern microscopy era, which is more data-driven and automated, and in particular enables these diverse correlative workflows and is collaborative. And Atlas V is one approach that we've seen with quite a bit of success in the past year or so in combining data sets, both spatially but also dictating and driving decisions about navigation tasks. Of course, it does a number of advanced acquisition tasks on the electron microscopy and focused ion beam platforms. But it then allows you also to overlay images, but also spatially register them. So you have a record. You effectively have a record of the context as kind of a sample-centric workflow where you have, as you acquire new information from the sample, it continually populates that model. And in the end, obviously, you want to understand through a quantitative technique of segmenting data sets and measuring various volumes. And I'd like to show this through the lens of just a couple of very quick studies in the coming couple of minutes where Atlas V is really playing a central midfielder position here between data sets but also instruments, and is actively steering the electron or ion microscopy platforms here, but it's taking in data from a number of different places to inform decisions for acquisition. And this is what it looks like. So the correlative workspace in Atlas V looks like this. This is actually one of Paul's samples here. This is one of the samples that we saw. We see a couple cracks running through. This circular inlay here is actually a three-dimensional X-ray microscopy data set. That's one virtual slice that we see in here, and in the background we see an SEM micrograph. But this could be populated with a number of other different modalities or subregions as well. And we've targeted a region in here. So this is really the main correlative workspace in the center, and then we can guide different tasks and different workflows on the left-hand side. You have a project-based viewer on the right-hand side, and down toward the bottom you have the utilization of these predefined protocols that allow you to basically identify a region of interest and perform more automated imaging tasks at given resolutions or modalities that are chosen. And so in doing so, what I will do here is skip forward, as I see we're getting toward the end of the hour, and walk you through this one example, taking a quick diversion away from specifically a battery material. Here we're looking at an aluminum alloy, some work done in collaboration with Arizona State University, where we're similarly here taking in a Versa data set here in yellow. And we're overlaying this with the 2D SEM image, and you see these bright features they turn out to be heavy metal iron-based inclusions primarily. But the beauty is that now we have the ability once these are spatially registered together, we're able to inspect the subsurface. So we found this void or low-density inclusion, and we need to be able to see the nanoscale structure that only a FIB-SEM can resolve for us. This goes beyond the resolution of what an X-ray microscope can achieve, and sure enough, we targeted that region, and we performed a FIB-SEM tomography around that void, and it turns out that was a silicon-bearing inclusion as well. So those tens of micron scale inclusions, which you see here as speckles in the full volume, so you have the full intact sample. It's about 6 millimeters in size. Take 6 micron voxel acquired on the Versa. We can non-destructively zoom in, get down to a micron or below voxel dimension, get quantification of those inclusions and volume percent and things like that. But you can now plan an imaging experiment and a targeted experiment to pick out individually possibly sparsely located inclusions and dig to that region of interest with already knowing, effectively having this roadmap of the X-ray microscopy data. So Atlas V allows you to perform that experiment. So this is some of the visualization. This is in the end the FIB-SEM stack. This is acquired here a few tens of microns in field of view here with a voxel and slice dimension here of around 10 nanometers. Of course, you can extend that below 10 nanometers. In this case, it was done approximately in that range. So with that, where does that lead? Why do we want that information? I mean, that information from that volume is essential to be able to quantify now that precipitate structure. So it turns out these are magnesium precipitates, and they decorate not only the grain boundaries of the aluminum, but they also are within the grains themselves. And pulling out basic statistics in a spatial context here is essential, and we want this information in the environment of that void that we found. And on first order, we found that approximately the same number of precipitates are inside the grain versus the grain boundary, but you have a very statistically significant difference in the volume and as well as the shape. And so this is just a quick snapshot of the type of quantification you can do, and you can draw conclusions about which, obviously, the ones at the grain boundary were most likely to nucleate first, as they have a lower activation barrier. So this is kind of the end of the chain here, but you could always perform this kind of targeted imaging at various regions here. I just wanted to show a snapshot here of the type of analysis that's also performed. Now we're in the midst of doing this on a number of other types of materials coming back to batteries. This was the subject of a webinar last year, I believe, with Timo Bernthaller's group in Germany, in Aalen, using a very similar approach to look at these inhomogeneities within, this is the Versa data set and a virtual slice. You pick these out and want to explore the chemical composition of these in more detail, and that was done through an EDS approach, but only after it had been aligned in Atlas V. Just skipping very quickly through this, coming back finally to the NCA cathode that Paul showed a little bit earlier, we're able to bring this also into the environment and pick out individual defects, perhaps. And once those defects or cracks or individual pores that were found within certain particles, we can go in and now in cross-section in a targeted way, knowing already what's below the surface and combining that with spectroscopy information. So with that, I think I wanted to simply conclude by saying that this is really the future of targeted, directed, multi-scale acquisition procedures in material science, but here specifically in energy materials. Atlas V really kind of sits at the core of this and is an enabler for more automation and can manage the data basically across instruments by bringing it into this correlative workspace, and it enables quite a bit of collaboration as well. So with that, I think I will conclude. I'll pass things back over to Nick, our moderator. If there are any questions as we're speaking, if we have a few minutes, feel free again to type in your questions to the box below. And thank everybody for their time today. And Paul and I, again, would be happy to take a few questions. Thanks again.
Okay, thanks. Thanks, Arno and Paul, for your presentation. So, yes, we do have a little bit of time. We're running slightly short on time, but we'll do our best to get through as many questions as possible. So, obviously, if you haven't yet submitted a question, then now will be the time to do so. But let's see what's come in so far. Question for you, Paul, from a Dr. Shearing at Medtronic. And he asks, he says in one of the slides you showed an image of the cathode and obtained cathode porosity. Now, how do you get porosity from an image, and does the instrument include software to calculate that porosity?
Yeah, sure. So that's from Dr. Chen. So thanks for that question. So actually, once you've got that three-dimensional image, there is a huge variety of different geometrical information that you can extract, and that varies from porosity through tortuosity through to volume-specific surface areas, as well as some more subtle microstructural metrics like particle size distribution of kind of pore necks. There's a really huge and very rich amount of information you can extract from that. And apologies, I didn't have a chance to go into that in any detail. Typically, for a porosity calculation, what we'll do is we'll take the three-dimensional image, we'll perform some binarization of that image to say what is the solid phase and what is the pore phase, and then it's just a simple question of doing a sort of pixel counting or volume pixel, voxel counting algorithm to work out what the porosity is. But actually, once that binarized image is in your working environment, there is a really huge variety of different microstructural metrics that can be extracted. Arno, right at the very end, showed some of the sort of very elegant software that's now available with the microscope. So perhaps, Arno, you're best placed to comment about the tools which you would recommend for doing that.
Sure. Yeah. I'll cover that briefly. So it wasn't shown really in detail in today's webinar, but actually that alignment procedure, I'd say it's a blend. It's a mixture of calibration steps. Obviously, if you're bringing in a three-dimensional data set, you have more degrees of freedom. We actually, in doing so, in bringing in the Versa data set, you actually perform a step that's quite simple and quite quick, and you actually lock that top surface of effectively what you constrain it to approximately what the SEM would view. So you actually take that top surface, which is approximately flat, and it doesn't have to be perfectly flat, but you match that to what you see in the SEM image, and you lock that position. It's then brought into the environment, calibrated to a length scale, and it allows for the user some adjustments to be made in either either expanding that image or shrinking that image as necessary. And it turns out you do see similar surface features typically in many modalities. And so you can align different features there. It allows you the flexibility to align those features and then lock that in place. It's typically a pretty quick exercise, taking a couple of minutes in typical experience, where the time saving, where you actually save, as anybody familiar with FIB-SEM tomography knows, it's once you're started, I think that's an investment then once you've started the FIB-SEM tomography, so you want to be sure where it is. So a quick investment in that alignment step where the user guides that process at the beginning is necessary, but then if you can target multiple regions there, the time savings or productivity savings at the end is quite beneficial. So I hope that answers the question. The second half of that question was like what types of data sets can be brought in. Essentially any type of image data, for the most part, can be brought in. I mean, lots of people take even just optical images, or even a cell phone image of your sample is the most crude step at the very beginning, as simply as just a navigation task. So any common image format can be brought in to the environment. It can be 2D, it can be 3D, like a TIFF stack data set that comes in as well.
Okay, that's great. Thanks, Arno. Another question come in, probably for you, Paul, asking what do you currently see as the greatest challenge in the multi-scale battery work that you've done? Is it refining the image procedures and methods, or is it improving the post-acquisition quantification work?
I think it's all of the above, actually. We're really keen and excited to push the spatial resolution down to the finest possible lens scale. Actually, when I was doing my PhD, I was focused on focused ion beam slice and view, and then we kind of increasingly being using X-ray microscopy in recent years, and now I'm coming full circle. Now that these correlative tools are so effectively combined in software like the Atlas V package that Arno said, we're really excited to revisit our focused ion beam experiment and go for very, very high resolution images that will give us that kind of finest lens scale understanding of, for example, chemical decomposition. So the thing that I think we're most excited about is really spanning all of those lens scales from nanometers through to millimeters. And there are challenges with the instrumentation. There's challenges with the data management for all of those things. At the moment, we are collecting in our lab in the order of sort of tens of gigabytes of X-ray images a week. So there's a challenge with storage, and there's definitely a challenge with the post-acquisition quantification. And I think that what we'll see in coming years is an increased automation of the whole imaging workflow to enable these sort of higher throughput experiments to become more routine.
Yeah, if I can jump in there real quick, Paul, to summarize that, and also come back to that initial question, which I actually diverted from briefly, on that analysis side, and like, for example, how you calculate porosity, and obviously you have to first start with the segmentation of the technique, but the examples that were shown typically in the slides today typically come from software after the reconstruction step, after it's segmented and then quantified in some manner. We often use Visual SI Advanced, which is a capability developed by a company named ORS, who we collaborate with quite closely, and it performs all sorts of different geometric analyses, but also performing segmentation. But really tying that link back to using that information to dictate the imaging strategies. You'll find out information once you've quantified the data, and oftentimes you'll want to go back and image it with a different microscope or at a different resolution on the same microscope. So we see that need quite a bit.
I'll just jump in and say one final thing in addition to that, Arno, because we haven't really touched upon it today at all, just for time limitations. But, of course, there's an enormous power in combination of our images that we're extracting from all these different modalities with computational simulations, so finite element or computational fluid dynamic simulations, which enables us to base our microscopic material simulations of flow or catalysis or diffusion or electrochemistry on real-life data. Historically, what we've done is we've taken a highly idealized morphology or a structure that we can draw in a CAD program and use that as the basis for our simulations. Now we're kind of leaving that behind because we have this fantastic multi-scale data that we can import into COMSOL or Fluent or ANSYS or any of the kind of main sort of CFD and finite element packages in order to solve those important simulations on real-life structures. So that's a really powerful area that I would also say is an exciting opportunity for the battery community and, in fact, for the materials community in general.
Okay, thanks, Paul. Probably time for a couple more questions, so we'll see how we get on. The next question asks, as you build imaging strategies that transverse scales, can you comment more on any necessary sample prep steps that you need to take for either batteries or other materials?
Arno, do you want to field that one?
Sure, yeah, I'll take a stab and feel free to jump in. Yes, of course, you need to sample. I showed the length scale connectivity plot more or less at the beginning, volumes versus resolution. And obviously, you can't get nanometer scale resolution within a sample that's the size of a meter. So at some point, you do have to extract smaller and smaller samples. To some extent, like in a lot of the data that Paul showed, you can do, interior tomographies where you're virtually zooming into the bulk of a volume and getting consecutively higher resolution. But that'll hit a limit, of course, some practical limits due to the amount of material that's outside of the field of view, basically contributing to the noise. So steps that have been taken, for instance, to create a sample for the ultra, which is typically much smaller, a few tens of microns, or even preparing all the way down to the focused ion beam, where you need to have basically a surface that's accessible. We've used a variety of techniques, including some laser techniques, some laser ablation techniques, some mechanical techniques, using various mechanical cutting techniques that are used. And actually, even the focused ion beam is used oftentimes to create pillars. We saw some pillars for compression studies there as well, and you could even use potentially the Atlas V workflow to basically identify a subsurface region and mill out a pillar or a sample approximately of a pillar shape to then place into the ultra. Is often used as well. So there's a variety. There's no one sample preparation step that is necessary. I think maybe if Paul, you want to mention very briefly on specific to batteries, because I know several of them, or you can't directly expose them to air in a safe way. Do you want to talk about any of the steps you've had to take?
Well, so we developed steps for encapsulation of air-sensitive materials, both for the Versa, and I showed an image there of an operating in-situ cell we developed, which is made out of a plastic part, PFA part, which is very X-ray transparent. So that's great. And the sample volumes that we're interrogating in the Versa are typically quite large. So that was a nice in-situ environment that we were able to look at operating materials. For the Ultra, where we're looking at encapsulating air-sensitive materials, again, we've used a variety of different plastics and glasses and PEEK polymer type tubes to encapsulate some of these very air-sensitive materials with some significant success. One of the big challenges historically has been sort of imaging batteries under any kind of operando or in-situ condition has been very difficult because you're always depackaging a battery and having to expose it to air before you can transfer it into your vacuum chamber for whatever analysis technique you're going to. With the X-ray microscopy, because we can conduct this encapsulation under a protective environment, we can then very readily transfer from the glove box into the Versa or into the Ultra to look at these materials in their correct chemical state.
Okay, thanks, Paul. Probably just time for one last question. It's a short question. I don't know if it'll be a short answer. But the question is, how do you detect different phases in the X-ray images?
Okay, so there are a couple of different mechanisms for detecting contrast between different material phases, so different chemical composition phases within a battery, which is great because oftentimes we're interested in composite materials for batteries and fuel cells and other things. On the Versa, you can do absorption contrast imaging, and we can vary both the energy of the X-ray beam, and we can also use a variety of different filters to change the instant X-ray beam before it sees the sample, and in doing that we can generate a variety of different absorption contrast maps. which we can then effectively combine using a tool called Discover. So we can take X-ray images on our lab source at many different combinations of X-ray energies in order to selectively highlight the different materials that go into making up our composite battery electrode. And so that's really very powerful, because this is now beginning to replicate the type of energy selective imaging that until very recently was only possible at synchrotrons. As well as the absorption contrast, we also have what we call phase contrast imaging capabilities, both in the Versa and the Ultra, where we have a propagation phase contrast and a Zernica phase contrast mechanism, respectively, which enables us to isolate even very low density materials based on the interaction with the X-rays and the phase shift that's caused by those materials. So there are a bunch of different tricks that we can play, and actually by doing this and combining the different images, we see this as a very powerful tool for looking at composite materials, including batteries and fuel cells.
Okay, thanks for that, Paul. Yeah, unfortunately we have run out of time, and we're slightly over time, so we apologise if you have somewhere else to be, but thanks for bearing with us today. And thank you for joining us, of course, and special thanks to you, Paul and Arno, for your presentations to us all today.
It's a pleasure. Thanks, everyone.
Thank you, Nick.
Thank you. Just as a reminder to everybody, the webinar has, of course, been recorded as usual, and it will be available for viewing in the next couple of days. And when that's ready, we'll send you an email with details on how to access that. In this on-demand version, there's also a feedback area, so if you think of any further questions or comments that you wish to put to Paul or Arno, then please feel free to do so, and they'll email you a reply in due course. But for today, as I said, that's everything. So from Paul Shearing, from Arno Merkel, and from me, Nick Taylor, it's goodbye. Bye-bye.